Hello, this is intended as a redoing of my video, Continuum Hypothesis, Case Still Open. Now, this is going to be done as a series, whereas that was one video. If you are still in May 2011 and I haven't pulled it yet, you can go and see my original Case Still Open video, but chances are, if you're seeing it at some point in the future, I may have pulled it by now. So I'm also going to be pulling a whole lot of other videos that are not related to mathematics, logic, philosophy. A lot of my other videos I'm just going to pull down. So enjoy them while you can, because a lot of those other videos are not going to be there. The reason being, I need to get back to the original focus of what this channel was all about. You know, even some of the science videos, I might just decide, you know, this is an overreach. So we're going to try to get back to the real focus of this channel, and that is a discussion of the continuum hypothesis and whether it's true or not. And I want to start off, first of all, I'm going to need to assume basic knowledge about the continuum hypothesis. Although in this intro video, I am going to give a kind of a background to it. But from here on out, I'm going to need to assume a basic familiarity with the concept. Bear in mind, there are going to be some assumptions I'm going to start off with. And one of those assumptions is that mathematics is real. That mathematical discoveries are real discoveries. That mathematics is not the playground of a cognitive elite that can simply set up axioms and then prove something from those axioms. And well, that's fine if that's how you want to play it, but the bottom line is that there is a real mathematical world, that the rational numbers exist, that the real numbers exist. Now, I'm not going to start off assuming that you know, all mathematics is constructible. I'm not going to start off with an assumption like that, but I am going to start off with the assumption that there is such a thing as mathematics, and that there is such a thing as infinity. Because if, you know, some of you out there who are mathematicians want to be finitists. You just want to say the finite is the only thing that exists. But what if I were to talk about the set of all finite sets? I mean, that you know, logically, right, there'd have to be a set of all finite sets. Well, if I were to have a set of, let's say, the number 1, 2, 3, 4, 5 as a set, and then the set of 6, 7, 8, 9, 10, that's a set. About 11, 12, 13, 14, 15, that's a set. Well, keep it on going, am I going to have a finite set? Think about it. If I keep on going forever, then that's an infinite set right there. So the set of all finite sets, that's not a finite set. So, I mean, right there, that whole argument is, to use a YouTube term, is pwned, okay? So, sorry, but if you accept finite, you accept infinite as a logical counterpart to what's finite. So I'm also going to assume that Cantor is correct, that the infinity of the real numbers is greater than the infinity of the rational numbers. Okay, and I'm going to have to assume that. And at the very beginning of this channel, I did a series where I went through the diagonalization argument, but I'm not going to review that for this series. I'm going to continue on from there. Now, for those who might not be familiar with these subjects but might want to follow this video along, let me just speak very briefly to you. Infinity as a paradoxical concept goes way back into history. I mean, the whole idea that forever is paradoxical, we'll trace one paradox at least back to Galileo. Let's look at two circles, a smaller circle and a bigger circle. And by the way, those of you who want to get into the continuum hypothesis right away, and there are other videos up there, you might want to skip ahead to them. Okay, so this is kind of to bring people up to speed a little bit. Okay, we have the smaller circle and the bigger circle, and notice I have the same center for both of them, and I have a bunch of lines going through both. Well, we have or actually they're rays. Okay, now I notice that I have a finite number of rays here. You'll notice that the same number of rays go through the smaller circle as the bigger circle. And if I were to add more and more rays, I would still have the same number of rays. And then more and more and more and more and more and more until we have an infinite number of rays going through the smaller circle, that same infinite number of rays is going through the bigger circle. Or looking at it the other way around, if I have an infinite number of rays going through the bigger circle, they fit, if you will, in the smaller circle. Okay, well, Galileo thought about it, and he suddenly realized, wow, that's very strange, because you would think that there's a bigger infinity and a smaller infinity, right? But actually, if you look at it in terms of boxes, and I have 1 box, 2 box, 3 box, 4 box, 5 box, 6 box, 7 box, 8 box, 9 box, 10 box, going on forever. And I took those boxes, and I counted them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to infinity. Well, let's say I were to take those boxes and double them up. Okay, I took the 1 and the 2, and I bunched them up. I took the 3 and the 4, and I bunched them up. The 5 and the 6, and I bunched them up. And I can then count my groups of double boxes. I have 1, okay, 2, 3, but that 1, 2, 3 actually corresponds to 2 different boxes that I've bunched together. So the 1 would correspond to the 1, 2, the 2 would correspond to the 3, 4, the 3 would correspond to the 5, 6, and lo and behold, I'd go on forever. Well, wait a second. There's something a little bit strange here. I didn't create any new boxes. Because as it is, it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to infinity corresponds to twice the amount of our boxes. In other words, it would seem to correspond exactly to what we would think would be 2 times infinity. And sure enough, it does, because I didn't create any new boxes. It's the same number of boxes, an infinite number of boxes. I could do the same thing with 3 boxes all bunched together, right? I would have 1 group of 3 boxes, 2 group of 3 boxes, 3 groups of 3 boxes going on to infinity. So I have an infinite number of groups of 3 boxes, but I started off with just an infinite number of 1 boxes. Almost as if I created an infinite number of boxes out of my hat. Well, what you're essentially showing there is that 2 times infinity is the same as infinity. 3 times infinity is the same as infinity. And actually, if you go as far as George Cantor, in the late 19th century, he demonstrated that in fact, you can extend that all the way from the natural numbers all the way out to the rational numbers. All rational numbers being, of course, ratios of integers. Okay, and he has a little proof that you can go to, and you can find it online. I'm not going to give it to you here, but he demonstrated that really infinity is uniform if you're talking about the accountable infinity, or infinity of counting numbers. But he demonstrated something very interesting. He had another proof that showed the infinity of the reals, and the reals included the transcendental numbers, or those numbers that were not algebraic. That the real numbers transcended the infinity of the reals transcended, or was uncountable with respect to the infinity of the naturals, or the infinity of all rationals. In other words, that all if not, which would be, or omega naught for those of you who like the Greek notation, but I'll call it aleph naught, would correspond to the rational numbers. But that the reals would be uncountable with respect to even the rational numbers. And this was an astonishing discovery, and the idea of levels of infinity was not universally liked by mathematicians. Now, the continuum hypothesis posited by Cantor stated that, in fact, that there is no level of infinity between that of the rationals and that of the real. That it's almost like a quantum level, even though quantum physics wasn't around yet when he posited this. That there was that there was almost like a leap from the infinity of the rationals to the infinity of the reals. Now, this was eventually shown to be undecidable with respect to set theory, and that's usually where the story ends, because undecidable, I guess, has to mean it isn't true. Well, I believe that there is an argument that can show that that will show that the case is indeed still open, and I intend to map that out if I can in this video series, and I hope that you'll enjoy it. I hope you'll stick with me. If my case still open video is still up there, go look at it. Go look at some of my previous videos. But if not, I'll carry you through it, maybe in a little more of a logically consistent manner than I have before. Thank you.